In the vast theater of the cosmos, where stars live out their brilliant but finite lives, few events rival the sheer violence and transformative power of a supernova. It is in these cataclysmic moments that neutron stars, some of the most enigmatic objects in the universe, are born. To understand what resides deep within the core of a neutron star, we must first trace back to its dramatic origins, a spectacular death marked by the collapse of a massive star and the explosive outpouring of energy known as a supernova. A star, in its prime, is a delicate balance between opposing forces. Gravity relentlessly pulls its mass inward, striving to crush the star into itself, while the intense heat and nuclear reactions in its core push outward, offering resistance and sustaining equilibrium over millions or even billions of years. This balancing act maintains the star's stability, allowing it to shine steadily as it fuses lighter elements into heavier ones, generating light and heat that radiate across the cosmos. However, this balance has limits, and the life of a massive star, those generally above 8 times the mass of our Sun, is a fleeting one. Over time, the star burns through its nuclear fuel, transitioning from fusing hydrogen into helium, then helium into carbon, and progressively heavier elements up to iron. Iron is the final straw. It cannot release energy through further fusion, unlike lighter elements. When the star's core becomes predominantly iron, the continuous outward pressure generated by fusion ceases. Without fusion's outward push, gravity gains the upper hand, initiating an unstoppable collapse. This collapse transpires at incredible speeds, shrinking the star's core tremendously, from thousands of kilometers down to barely tens of kilometers in diameter. Within seconds. During this implosion, temperatures soar to billions of degrees, and densities spike to unfathomable extremes. It is here that the fundamental structure of matter is forced to undergo radical changes. As the core compresses, protons and electrons are squeezed together in a process called neutronization, producing a staggering flood of neutrons and an emission of neutrinos, elusive particles that flood the universe but interact weakly with matter. This transformation leads to an ultra-dense ball of neutrons, the nascent neutron star, a remnant that contains more mass than our Sun, compressed into a sphere about the size of a city. But the drama does not end with the core's collapse. The imploding outer layers of the star slam into this newly formed neutron core and rebound outward, generating a shockwave so potent it tears through the star's outer atmosphere. This shock is often revitalized by the intense flux of neutrinos streaming from the dense core, helping to propel the violent explosion we observe as a supernova. The energy unleashed in this explosion outshines entire galaxies for a brief moment, dispersing the stellar envelope into space and seeding the cosmos with elements forged in the star's fiery heart. This violent crucible leaves behind the compact neutron star, surrounded by expanding chaos. Some of these neutron stars become pulsars, emitting beams of electromagnetic radiation detectable as rhythmic pulses. Others may spin rapidly or harbor incredibly strong magnetic fields, becoming magnetars. Each neutron star holds an interior that remains deeply mysterious, where matter exists in forms yet to be fully understood. Appreciating this cataclysmic birth underscores the immense forces shaping neutron stars. It is a saga of intense gravity, nuclear physics pushed to its limits, and the interplay of particles under conditions beyond ordinary comprehension. The death of a massive star is not merely an end, but a transformation, giving rise to one of the densest objects known, whose core challenges our very understanding of matter. As we move deeper into exploring these dense remnants, tracing the journey inward from their surfaces to their cores, we will uncover layers of complexity hidden beneath their crusts. Yet, all this begins with the star's collapse and the supernova's explosion, a cosmic event that marks both an ending and a beginning, revealing a universe in constant flux and transformation. Imagine embarking on a voyage unlike any other, a journey not across distant lands, but deep into the heart of one of the universe's most enigmatic objects, the neutron star. Leaving behind the familiar surfaces of planets and stars, we navigate inward through realms where matter itself begins to defy our everyday intuition, transforming into exotic states that challenge even the brightest minds in physics. This is the passage from matter as we know it, through layers wrought by extreme pressures and densities, culminating in a core shrouded in mystery. At first glance, a neutron star might seem deceptively simple, a small, incredibly dense sphere about 20 kilometers in diameter. Yet this compactness conceals a staggering complexity, a layered interior where conditions change rapidly and matter assumes exotic forms. Our journey inward begins at this star's outermost surface, the crust, a realm already far removed from any earthly environment. The crust, roughly a kilometer thick, is an ultra-dense lattice of atomic nuclei, packed so tightly their separations are minuscule compared to atoms we encounter on Earth. Here, electrons swarm in a sea between nuclei, free from atomic orbitals. The pressure is so immense that atoms lose their electrons in a process called ionization, and the matter exists as a solid crystal of nuclei embedded in a degenerate electron gas. This starkly contrasts with terrestrial matter, where atoms maintain their discrete shells and electrons cling closely to their nuclei. Moving beneath the crust, pressure and density increase precipitously. The crust gives way to the outer core, a mysterious, fluid-like region where atomic nuclei dissolve entirely. In this exotic soup, matter transforms. The familiar protons and neutrons swim freely within a dense sea of neutrons, interspersed with a trickle of protons and electrons to maintain electrical neutrality. The atoms we understand vanish here, replaced by nuclear matter under conditions that are impossible to replicate on Earth. Further inward, deeper still into the inner core, we broach the frontier where fundamental physics is pushed to its extremes. The very nature of matter may fundamentally change. Some theories suggest the existence of strange matter, a form involving strange quarks, unusual constituents not stable in ordinary conditions, but perhaps energetically favored under ultra-high density. Others propose that quarks themselves, normally bound tightly together within protons and neutrons, could become deconfined, forming a quark-gluon plasma, a primordial state of matter only glimpsed fleetingly in particle accelerators. Our knowledge of this inner sanctum is primarily theoretical, constrained by the laws of physics as we understand, and the limited indirect observations we can make. The pressures there are thought to exceed 1 billion tons per square centimeter, and densities may reach several times that of an atomic nucleus. Within this core, gravity and quantum mechanics coalesce in ways that challenge the boundaries of modern science. The journey inward is not just a descent through density and pressure, but a transition through phases of matter that progress from crystalline solids to superfluid and superconducting states to potentially alien phases where the concepts of individual particles dissolve. It illustrates a profound narrative, how elemental constituents assemble and transform under the universe's most intense conditions. Contemplating this journey deepens our appreciation for the delicate balance that defines neutron stars, between gravity striving to compress and quantum forces wrestling to resist collapse. Each layer acts as a sentinel guarding profound secrets encoded in the behavior of matter under pressure so immense it forces physicists to extend their theories and explore novel physics. As we prepare to delve further into the defining attributes of these layers, exploring their structure and the physics at play, it becomes clear we stand at the crossroads of knowledge and mystery. The journey from matter to mystery inside a neutron star is a microcosm of the bigger cosmic quest. Understanding the fundamental nature of the universe by studying its densest, most extreme objects. This quest continues to unfold, chapter after chapter, in the layers under the neutron star's surface, inviting us ever further into the astounding depths of reality. To truly grasp the nature of neutron stars, one must come to terms with their staggering densities, a realm so far removed from our everyday experience that it challenges both imagination and scientific understanding. When we discuss density, we're speaking of the amount of mass packed into a given volume. On Earth, densities span a familiar range, from the lightness of air at approximately 0.0002 grams per cubic centimeter to the compactness of metals like iron at around 7.8 grams per cubic centimeter. Now, picture matter compressed to millions or even billions of times greater densities. This is the world inside a neutron star's core. A neutron star embodies one of nature's most extreme states. A celestial sphere where an amount of mass greater than that of our Sun is squeezed into a sphere roughly 20 kilometers in diameter, roughly the size of a medium-sized city. This condensation means that a sugar cube-sized amount of matter from a neutron star would weigh about 1 billion tons on Earth. To frame this comparison further, consider that ordinary matter around us, the very fabric of our bodies, the earth beneath our feet, the air we breathe, is staggeringly less dense by comparison. But how does the density inside a neutron star's core compare to something as dense as an atomic nucleus itself? Nuclei, the tiny hearts of atoms, are already unbelievably dense. For example, an atomic nucleus's density hovers around 2.3 x 1014 grams per cubic centimeter. Yet, inside the neutron star's core, densities can soar to 2 or 3 times that of nuclear matter, sometimes even greater depending on the star's mass. This compression packs matter so tightly that the familiar distinctions between individual protons and neutrons may begin to blur. The difference between neutron star core matter and ordinary matter is staggering not just in magnitude, but in kind. Earthly matter is predominantly arranged in atomic structures, nuclei surrounded by electrons in defined shells, interacting through electromagnetic forces that govern chemistry and biology. In contrast, the core of a neutron star is a quantum crucible, where nuclear and subnuclear particles intermingle under gravity's supreme compression in a state unlike anything else observable elsewhere in the universe. This immense density translates to extreme pressure. For context, the pressure at the center of a neutron star can reach more than 1035 pascals. That's about 1 trillion times the atmospheric pressure on Earth. Under such crushing pressure, the very fabric of matter is pushed beyond ordinary limits. Electrons are forced into protons to form neutrons, creating a dense, neutron-rich fluid. This process, neutronization, leads to matter becoming neutron-dominated, a stark departure from the electron-rich atomic matter we know. Visualizing these densities also helps in understanding why neutron stars don't collapse into black holes, at least not immediately. There exists a subtle but powerful pressure derived from the Pauli exclusion principle, which asserts that no two neutrons can occupy the same quantum state simultaneously. This degeneracy pressure, along with the repulsive components of nuclear forces, counteracts the relentless inward crush of gravity, lending the neutron star a tight balance that enables it to survive as a compact object rather than collapsing entirely. To further appreciate the scale, Consider the Sun itself, which has an average density of just about 1.4 grams per cubic centimeter, comparable to some light metals on Earth. A neutron star's core, by contrast, is packed hundreds of trillions of times more densely. If the Sun were compressed into this density, it would be no larger than a city's diameter. Yet, neutron star densities extend beyond simple compression of familiar particles. The pressures and densities in the inner core may lead to new forms of matter, such as hyperons, particles containing strange quarks, or even deconfined quark matter. While these exotic states remain theoretical, their possibility highlights how neutron stars are laboratories for physics under conditions unachievable on Earth. In summary, the journey from the familiar densities of everyday matter to the unimaginable densities inside neutron star cores is a voyage across many orders of magnitude, a traverse from the tangible world into a domain dominated by fundamental nuclear and quantum forces. This stark contrast is critical to understanding how the composition, behavior, and evolution of neutron stars are shaped. The comparison underscores how neutron stars bridge the microscopic and cosmic realms, compressing the universe's secrets into an incredibly tight, mysterious core. As we move forward, this understanding of density sets the stage for exploring the detailed internal structure of neutron stars, how the crust, outer core, and inner core differ, and what physical principles govern each layer. The density story is only the beginning, a gateway to deeper mysteries of matter itself. Delving deeper into the intricate anatomy of a neutron star, we uncover a remarkable stratification, a layered composition that narrates the story of matter under extreme conditions. Much like the Earth, with its crust, mantle, and core, a neutron star, too, possesses a sophisticated internal structure. Yet, unlike any terrestrial body, its layers hold exotic states of matter governed by nuclear physics and quantum mechanics at their limits. To truly appreciate what lies hidden within such a compact object, we must explore the defining characteristics of its three principal regions: the crust, the outer core, and the inner core. Starting at the surface, we encounter the crust, a relatively thin but extraordinarily dense shell spanning roughly 1 kilometer in thickness. Though minor in scale compared to the entire star, this layer is fascinating in its complexity and composition. The crust can itself be subdivided into an outer and inner region based on the density and arrangement of its constituent particles. In the outer crust, matter exists in the form of a crystalline lattice of atomic nuclei, densely packed together with electrons moving freely among them. These nuclei are neutron-rich isotopes, versions of elements heavier and more neutron-laden than those typically found on Earth. This results from the extreme pressure that forces electrons to be captured by protons, increasing the neutron fraction within nuclei. The positively charged nuclei array themselves in a regular pattern, a solid lattice akin to crystal structures familiar in earthly minerals, but compressed to mind-boggling densities. The electrons form a degenerate gas, a quantum sea where electrons fill available energy states up to very high energies, exerting pressure to counterbalance gravity. Progressing deeper toward the inner crust, we reach densities approaching the so-called neutron drip threshold, where neutrons begin to escape from nuclei, no longer bound within them. Here, the landscape transforms into a hybrid, nuclei immersed in a sea of free neutrons and degenerate electrons. This peculiar mix is unique to neutron stars and marks the boundary between nuclear matter and free neutron fluid. The competition of forces in this region results in fascinating shapes sometimes described as nuclear pasta, due to their resemblance to lasagna sheets, spaghetti strings, or gnocchi clumps. Exotic configurations emerging from the interplay of nuclear attraction and Coulomb repulsion that minimize the system's energy. This whimsical terminology underscores the peculiar states matter can assume under such conditions. Beneath the crust lies the fluidic outer core, where the concept of traditional nuclei dissolves entirely. Here, densities soar beyond the nuclear saturation density, roughly 2.8 x 1014 grams per cubic centimeter. In this environment, protons and neutrons lose their individuality, merging into a uniform, strongly interacting nuclear fluid dominated by neutrons, but containing a minority of protons and electrons to maintain charge neutrality. This dense nuclear soup teeters on the edge of incomprehensibility. Particles behave collectively, and quantum phenomena become paramount. At these depths, neutrons may exhibit superfluidity, a state of matter flowing without viscosity, while protons might enter a superconducting phase, conducting electric currents without resistance. These quantum states profoundly affect the star's thermal conductivity, rotational dynamics, and magnetic characteristics. Continuing inward, we approach the inner core, the deepest and most mysterious realm. Unlike the more definitively characterized outer layers, the inner core exists in a regime of densities and pressures at or above several times nuclear saturation density. At such extremes, nuclear models become less certain, and new exotic forms of matter could manifest. Theorists have proposed the emergence of heavier baryons, known as hyperons, particles containing strange quarks uncommon in ordinary matter. Alternatively, the inner core may harbor deconfined quark matter, a state where quarks, normally confined inside protons and neutrons, roam freely within a quark-gluon plasma. This phase transition, if it exists, represents a profound shift in matter's fundamental nature, akin to water freezing into ice, but on an unfathomably more extreme scale. Exploring the inner core also opens the door to quantum chromodynamics in extreme conditions and possible states such as color superconductivity, which influence properties including equation of state, the relationship between pressure, density, and temperature. These interior characteristics ultimately govern the neutron star's mass-radius relationship and stability. From surface to core, a neutron star's structure exemplifies a remarkable journey through phases of matter, transitioning from crystallized nuclei bathed in electrons to neutron-rich fluids, and possibly reaching exotic quark matter at its center. Each layer informs us about the microphysical interactions that counterbalance gravity's immense force, enabling these stars to resist collapse and yet remain some of the densest objects in the universe. In the coming discussions, we will examine the nature of pressures and forces that defy our capacity to visually conceptualize and how these internal layers work in concert to produce the macroscopic phenomena observed in neutron stars. Understanding these layers provides the essential scaffolding to grasp the behavior of ultra-dense matter, a key to unlocking the mysteries hidden in neutron star cores. To fully comprehend the inner world of a neutron star, we must grapple not only with matter compressed beyond ordinary limits, but also with scales of pressure and gravity so vast they defy human intuition and visualization. The sheer intensity of forces within a neutron star is unlike anything we encounter on Earth or even in most cosmic environments. To understand how gravity and pressure interact at such extremes, we must expand our perspective beyond everyday experience and explore the fundamental principles shaping these astonishing stellar remnants. First, let us consider gravity, the silent architect of neutron stars. Gravity's strength on a neutron star is magnitudes beyond that at Earth's surface. While Earth's gravitational acceleration is approximately 9.8 meters per second squared, a neutron star's gravitational pull at its surface can exceed 211 times this value. Imagine a force attempting to crush every particle towards the star's center with an intensity so fierce it would accelerate an object equivalent in mass to a bowling ball to near light speed in just a fraction of a second if left unopposed. This immense gravitational field emerges not only because of the star's mass, which is typically around 1.4 times that of our Sun, but primarily because of its tiny radius, roughly 20 kilometers, compacting all that mass into a region the size of a city. This incredible density warps the very fabric of space and time according to Einstein's general relativity, causing time to slow noticeably when viewed from a distant observer and bending light paths around the star. Such relativistic effects are not just theoretical musings. They are key to interpreting the signals we observe from neutron stars, such as pulsar emissions. Alongside this intense gravity lies pressure of truly unfathomable scale. Pressure, simply put, is force per unit area. On Earth, we are familiar with air pressure at sea level, about 325 pascals, or roughly 14.7 pounds per square inch. The core of a neutron star, however, generates pressures surpassing 1034 pascals, exceeding terrestrial atmospheric pressure by a factor of at least 1 billion trillion. This pressure results from the star's own matter resisting gravitational collapse. The particles within are packed so densely that quantum mechanical effects come into play, providing degeneracy pressures that act as a counterbalance to gravity. Quantum degeneracy pressure arises from the Pauli exclusion principle, a fundamental tenet of quantum mechanics, which states that two fermions, particles like neutrons, protons, and electrons, cannot occupy the same quantum state simultaneously. In neutron stars, the density forces these fermions into high momentum states, creating a powerful pressure that opposes further compression. This quantum resistance is vital in stabilizing neutron stars against total gravitational collapse into black holes. But quantum forces alone are not the whole story. At the densities found in neutron star cores, nuclear forces, residual interactions that bind protons and neutrons within nuclei, come into play on macroscopic scales. These forces can switch from attractive to repulsive at extremely short distances, adding yet another layer of complexity to the star's internal pressure balance. Visualizing these conditions challenges conventional analogies. If Earth's atmosphere were compressed to neutron star densities, the entire planet would shrink to the size of a single grain of sand under a crushing force that humans cannot even conceive. Even imagining the pressures at play is daunting. Consider a force so intense it could balance the weight of Mount Everest, yet concentrated on an area no larger than an atomic nucleus. Gravity and pressure in neutron stars exist in a delicate tug-of-war, maintaining a precarious equilibrium. Should the star's mass exceed a threshold, known as the Tolman-Oppenheimer-Volkoff limit, this balance would fail, and the star would collapse into a black hole, an object where gravity overwhelms all known forces. The incomprehensible scales of gravity and pressure within neutron stars also influence phenomena observable from Earth. For instance, their gravitational wells allow them to accelerate particles to incredible speeds, produce intense magnetic fields billions of times stronger than Earth's, and generate radiation detectable across the electromagnetic spectrum, including X-rays and gamma rays. Additionally, the extreme gravity slows time noticeably near the star's surface, a phenomenon known as gravitational time dilation, adding another dimension to our understanding of these objects. In summary, the astonishing forces inside neutron stars challenge not just physics, but our ability to visualize nature's extremes. The tremendous pressures and gravity compress and shape matter in ways that verge on the limits of scientific comprehension and human imagination. Yet, it is in exploring these extremes that we gain valuable insight into the fundamental workings of the universe. As our understanding advances, propelled by both theoretical modeling and astrophysical observations, we step closer to unraveling how these immense forces sculpt the internal landscapes of neutron stars. This journey prepares us to explore the fascinating interplay of particles under such conditions, as neutronization reshapes protons and electrons, and the star's core reveals quantum secrets still hidden from our grasp. As we venture deeper into the enigma that is the neutron star, one of the key transformative processes shaping its very essence is neutronization. This process, pivotal in the star's evolution from a dense stellar remnant to a neutron star, radically alters the composition of matter, converting protons and electrons into neutrons, and thereby sculpting the interior into an extraordinarily neutron-rich realm. To unravel what lies deep within the core, we must first understand how this transformation unfolds under the crushing gravity and intense density of these stellar remnants. At the heart of neutronization lies the interplay of fundamental particles: protons, electrons, neutrons, and neutrinos. In ordinary matter, protons and electrons exist in balance, forming atoms with electron clouds encircling positively charged nuclei. But the extreme conditions inside a neutron star dismantle this familiar order. As gravity relentlessly compresses the star's core during the supernova stage, and thereafter, matter is forced into higher densities and pressures where the usual distinctions between particle states begin to fade. The intense compression drives electrons to ever higher energies. As the density increases, electrons become so energetic that they are pushed into increasingly tight quarters with protons. When the density surpasses a critical threshold, roughly a few times the density of a conventional atomic nucleus, it becomes energetically favorable for protons and electrons to merge. This fusion occurs via a process known as inverse beta decay, or more precisely electron capture. A proton in the nucleus captures an electron, transforming into a neutron and emitting a neutrino in the process. The basic reaction can be summarized as follows: proton plus electron yields neutron plus neutrino. Mathematically, this reaction is written as P plus ek and plus one. Here, the proton, P, and electron, E, combine to form a neutron, N, and emit an electron neutrino, Na. The neutrino, a near massless and weakly interacting particle, escapes the star almost unimpeded, carrying away excess energy and lepton number. This steady conversion of protons and electrons to neutrons reshapes the star's interior, leading to the iconic neutron-rich composition that defines neutron stars. It's a dramatic shift, from matter largely made of protons and electrons to matter overwhelmingly dominated by neutrons. By the time neutronization completes, the star's core is a near-pure neutron fluid, a quantum system bound tightly by nuclear forces, but without the familiar atomic structure. The rate of neutronization hinges delicately on temperature, density, and the interplay of fundamental forces. In the core collapse during a supernova, neutronization proceeds rapidly, pumping a torrent of neutrinos outward. Neutrinos so numerous and energetic they temporarily trap themselves in the star's interior before escaping, impacting the dynamics of the explosion itself. This flux can equate to as much energy as that burnt by the visible supernova light, underscoring the process's energetic significance. Outside the core, in less dense regions, matter retains some protons and electrons, but as you plunge deeper, neutronization becomes increasingly complete. The star's crust, while still consisting of nuclei rich in neutrons, still preserves a lattice-like structure. Moving inward beyond the inner crust, the drop in free protons and electrons is dramatic. Neutrons dominate as a superfluid, flowing without friction, and further complicating the star's interior dynamics. Moreover, the formation of neutrons itself is facilitated by the Pauli exclusion principle. Since electrons and protons fill all available lower energy states at these densities, the only quantum mechanically allowable path to reduce the star's energy is the conversion into neutrons, which occupy a different set of quantum states. These quantum constraints maintain a finely tuned balance of particle populations, governed by chemical potentials, the effective energies balancing creation and annihilation, that determine the relative fractions of neutrons, protons, and electrons as density evolves. Neutronization also sets the stage for other exotic processes deeper within the core. The neutron-rich environment facilitates the emergence of particles containing strange quarks, hyperons, and possibly the deconfinement of quarks themselves, unlocking forms of matter far beyond ordinary nuclear physics. These possibilities arise because conventional nuclear forces become insufficient to hold matter together as density increases, nudging matter into new quantum states. Understanding neutronization is not only critical for grasping the star's internal composition, but also illuminates aspects of neutron star cooling and evolution. Neutrino emissions resulting from ongoing neutronization during early neutron star life significantly contribute to thermal energy loss, enabling the star to cool over timescales of thousands to millions of years. The neutron's superfluid state alters heat capacity and surface thermal conductivity, influencing observable properties such as thermal X-ray emissions. In sum, neutronization is a fascinating dance of particles, energy, and fundamental physics sculpted by the intense conditions within a neutron star's depths. It marks the transformation of ordinary matter into something profoundly alien, a neutron ocean sustained by nuclear and quantum forces with its own unique rules and behaviors. As we move forward, exploring physics beyond neutron degeneracy, we will uncover how these neutron-rich environments give rise to even stranger states of matter, revealing the fundamental fabric of our universe hidden deep within these stellar remnants. Venturing beyond the realm of neutronization, we arrive at the heart of one of the greatest challenges in astrophysics and nuclear physics alike: understanding the fundamental behavior of matter when compressed beyond neutron degeneracy. This domain lies at the core of neutron stars, where densities and pressures rise to levels so extreme that conventional physics pushes against its limits, and the mysteries of the quantum world reveal themselves in dramatic and exotic ways. To begin with, let us recall what neutron degeneracy pressure entails. It is rooted in the Pauli exclusion principle, a quantum mechanical rule that forbids identical fermions, specifically neutrons in this context, from occupying the same quantum state simultaneously. This principle generates a quantum pressure that resists further compression of neutrons following the collapse of the progenitor star. However, neutron degeneracy alone cannot fully define the equation of state, the detailed relationship between pressure, density, and temperature in the core of neutron stars. At increasing densities, other interactions and fundamental forces come into play. As matter is pushed beyond the density of atomic nuclei, the strongly interacting particles, neutrons and protons, no longer behave as isolated entities. Instead, the nuclear forces that govern their interactions are affected by extreme conditions, causing the effective interaction strengths to morph. Here, many body effects and complicated strong force dynamics dominate. These include repulsive short-range forces that become increasingly significant, adding to the pressure-resisting gravitational collapse. A remarkable aspect in this limiting regime is the possible emergence of new particle species, particles that are unstable or non-existent under normal terrestrial conditions, but may become energetically favorable inside a neutron star. Among these, hyperons, particles similar to neutrons and protons but containing strange quarks, are prime candidates. Their appearance would alter the particle composition profoundly and soften the equation of state, potentially affecting the maximum mass the neutron star can support before collapsing into a black hole. Meanwhile, the interplay of quark matter theorizes an even more radical shift. Instead of discrete neutrons and protons, quarks, the fundamental building blocks of baryons, may become deconfined, creating a quark-gluon plasma. This state resembles conditions only moments after the Big Bang or recreated briefly in particle accelerators, such as the Large Hadron Collider. In the deep core of a neutron star, where densities could exceed several times that of nuclear saturation density, such exotic phases may exist naturally and sustainably. Moreover, under these conditions, the matter may demonstrate remarkable quantum coherence effects. For instance, superfluidity and superconductivity, states in which particles move collectively without friction or electrical resistance, may emerge within the core. Superfluid neutrons form vortices that influence the star's rotation and glitch phenomena, sudden shifts in pulsar spin rates observed with great precision. Cooper pairing of protons in superconducting states influences the star's magnetic field evolution and thermal properties. Fundamental physical theories like quantum chromodynamics, QCD, governing the interactions of quarks and gluons, play a central role in predicting these states, but are extremely difficult to solve precisely under such dense and cold conditions. This leaves the physics of the neutron star core at the frontier where theory meets uncertainty, with multiple models competing to describe the elusive equation of state. This uncertainty reflects directly on astrophysical observables, mass-radius relations, tidal deformabilities detected via gravitational waves, thermal emissions, and rotational behaviors. Additionally, the behavior of matter at these densities invites the exploration of modified gravity theories and speculative physics beyond the standard model. Some hypotheses suggest exotic condensates or particle states may arise, while others wonder if unknown forces or particles could manifest under such conditions. Such speculation remains tentative, but neutron stars serve as natural laboratories, testing our most fundamental theories. In essence, beyond neutron degeneracy lies a quantum frontier, where strong nuclear forces, extreme density, and quantum statistical effects intertwine. This regime stretches our understanding from the familiar nuclear physics of laboratory experiments to the cosmic scales of stellar remnants. It is a realm where individual nucleons dissolve, new particles arise, and matter undergoes transformations that ripple out to shape observable properties of neutron stars. As we continue our exploration into the core, the journey from neutron degeneracy leads naturally to the study of exotic quantum states, superfluidity, and superconductivity. Intricacies that dictate much of neutron star dynamics and offer tantalizing clues about matter's behavior at the universe's most extreme thresholds. Deep within the compact depths of a neutron star, conditions become so extreme that matter behaves in ways completely alien to our everyday experiences, giving rise to some of the most exotic quantum phenomena known in physics: superfluidity and superconductivity. These phenomena don't just represent esoteric curiosities. They are fundamental to understanding the internal dynamics, thermal evolution, and magnetic properties of neutron stars. To appreciate their significance, we must first explore what these states mean and how they emerge amid the crushing pressures and extreme densities of a neutron star's core. Superfluidity is a phase of matter where certain particles can flow without viscosity, essentially without any internal friction that would normally impede movement. This remarkable property was first discovered in liquid helium cooled to near absolute zero on Earth, but in neutron stars, it unfolds on a cosmic scale under vastly more extreme conditions. Within the core, the neutrons themselves pair up in a manner reminiscent of electron pairing in superconductors, forming what is called Cooper pairs. These pairs behave collectively as a coherent quantum state, enabling the neutrons to move as a superfluid. Simultaneously, protons within the core possess their own fascinating quantum state, superconductivity. Superconductivity refers to the ability of charged particles to conduct electricity without any resistance. Just as electrons pair up in conventional superconductors, in the dense nuclear fluid inside neutron stars, protons form Cooper pairs that circulate current without energy loss. The presence of superconducting protons has profound implications for the star's magnetic field, contributing to its extraordinary strength and affecting how that field evolves over time. The formation of these states is governed by quantum mechanics and many-body physics under extreme conditions. At the immense densities encountered, several times that of atomic nuclei, neutron-neutron and proton-proton attractive interactions induce pairing, overcoming thermal agitation despite the core's high temperature relative to Earth standards. These quantum condensates profoundly influence the neutron star's transport properties, such as heat capacity and thermal conductivity, directly impacting how the star cools over time. Moreover, superfluidity within the neutron star core plays a critical role in the star's rotational dynamics. Neutron stars are known for their rapid spins, sometimes rotating hundreds of times per second. The superfluid neutrons inside do not rotate uniformly like a rigid body, but form a complex array of quantized vortices, tiny whirlpools around which superfluid circulation occurs. These vortices can pin to the star's crust or migrate, leading to sudden changes in the star's rotation rate, phenomena observed as glitches in pulsars. These glitches provide one of the most compelling observational signatures of superfluid behavior in neutron star interiors. On the superconductivity front, the proton condensate allows the magnetic field to thread the star in quantized tubes called fluxoids. This vortex fluxoid system defines a subtle interplay between rotation and magnetism inside the core, influencing the star's magnetic evolution and stability. The extremely strong magnetic fields of neutron stars, sometimes trillions of times stronger than Earth's, are likely shaped in part by these superconducting properties. Interestingly, there is growing theoretical evidence that the neutron star core might host even more exotic pairing states, such as phases with anisotropic or non-conventional pairing symmetries. These states may affect neutrino emission rates, modifying how quickly the star loses energy and cools. Understanding these nuanced quantum states demands a blending of nuclear physics, quantum field theory, and astrophysical modeling. The coexistence of superfluidity and superconductivity in neutron stars is exceptional because it merges neutral and charged particle condensates in one coherent quantum fluid, a state difficult to replicate in terrestrial laboratories. Experimental evidence for these effects comes indirectly from astrophysical observations, including thermal emission patterns, pulsar spin irregularities, and cooling curves of young neutron stars. Thus, as we peer deeper into neutron star cores, these quantum states represent both a window into the behavior of matter under extreme conditions and a key to unlocking the mysteries of neutron star phenomenology. They highlight how familiar physical principles, taken to the extremes, produce extraordinary consequences, shaping the lives and observable features of these stellar remnants. As we continue exploring, the role of neutrinos and their interactions within these bewildering environments beckon next. For neutrinos are not just passive bystanders. They are vital messengers and energy carriers that influence the star's cooling and evolution. Understanding their subtle dance with matter under such dense conditions will further illuminate the exotic physics within neutron stars' cores. Deep within the enigmatic core of a neutron star, neutrinos play a silent but profoundly influential role that extends far beyond their elusive, ghost-like reputation in particle physics. These nearly massless, uncharged particles are born in staggering quantities during the star's formation and continue to shape its evolution through their subtle interactions with ultra-dense matter. To appreciate their role, we must delve into how neutrinos are produced, how they navigate the star's extreme interior, and what their escape means for the neutron star's life and observable properties. Neutrinos emerge as a natural byproduct of the neutronization process, where protons and electrons combine to form neutrons under intense gravitational compression, emitting electron neutrinos in the process. The core collapse of a massive star during a supernova is a cacophony of these neutrino emissions, releasing vastly more energy in neutrinos than in electromagnetic radiation. In fact, neutrinos carry away about 99% of the gravitational energy released, totaling approximately 10^53 ergs, which is equivalent to the sun's energy output over billions of years concentrated into a matter of seconds. However, the journey of neutrinos escaping from such conditions is not straightforward. Despite their typically weak interaction with matter, the densities inside neutron stars are so extreme, billions of times denser than atomic nuclei, that neutrinos can be temporarily trapped, scattering repeatedly against neutrons, protons, and electrons. This creates a neutrino opacity zone, sometimes termed a neutrinosphere, analogous to the photosphere of a star for light, where neutrinos last interact strongly before escaping into space. The neutrino mean free path in these regions is dramatically shortened, meaning neutrinos diffuse outward rather than streaming freely. The diffusion of neutrinos plays a crucial role in the neutron star's thermal and dynamic evolution. As they gradually escape over seconds to minutes after formation, neutrinos cool the nascent neutron star considerably, carrying away thermal energy and influencing the temperature gradients inside. This cooling affects the behavior of matter, the formation of quantum condensates such as superfluid phases, and the star's thermal profile observed later through X-ray and other electromagnetic emissions. Beyond their cooling influence, neutrinos partake in complex interactions that influence the neutron star's chemical equilibrium and composition. Through processes like neutrino absorption and scattering, they help maintain the delicate balance of particles, neutrons, protons, and electrons, within the dense core. Neutrino interactions also have implications for how quickly neutron stars settle after the violent birth in a supernova, and how their magnetic fields and velocities develop, sometimes imparting so-called kicks that send neutron stars hurtling through space. As neutron stars age and cool, neutrino emission patterns change. In the long-term cooling phase, processes such as the modified Urca and direct Urca reactions dominate, which involve neutrino emissions through beta decay and inverse beta decay interactions within the dense matter. These reactions can proceed more or less efficiently depending on the star's internal composition, directly affecting cooling rates. Observations of young neutron stars' thermal emission provide constraints on these microscopic processes, linking neutrino physics to astrophysical measurement. Moreover, neutrinos arising from neutron star mergers, the catastrophic collisions of neutron stars, have captivated astronomers and physicists alike, as these events produce intense neutrino fluxes alongside gravitational waves and electromagnetic signals. Neutrino detection from such mergers, while challenging, offers a new window into the dense matter physics and nuclear reactions beyond what can be gleaned from isolated neutron stars. In sum, Neutrinos occupy a unique position as both subtle messengers and active participants in the dense stellar interiors. Their interactions, escape dynamics, and energy transport shape the thermal, chemical, and dynamic footprints left by neutron stars. Through detailed observation and modeling of neutrino behavior, we venture closer to deciphering the mysteries locked deep within these extraordinary cosmic objects. Moving forward, we will uncover further layers of neutron star complexity by exploring the structure of their crusts and mantles, where matter assumes unexpected forms, aptly named nuclear pasta, adding yet another intriguing chapter to our understanding of matter under extreme conditions. As we penetrate deeper into a neutron star, moving beyond the relatively familiar notions of ultra-dense matter, we encounter one of the most captivating and visually evocative concepts in astrophysics: nuclear pasta. Though it might sound whimsical or even culinary, nuclear pasta refers to a range of exotic, complex phases of matter that exist in the crust and mantle of neutron stars. These phases reveal the profound and often surprising ways in which matter organizes itself under immense pressures and densities. To truly understand what nuclear pasta entails and why it matters, we need to unravel how the intricate dance of nuclear forces and Coulomb repulsion shapes this extraordinary microstructure. At densities approaching and surpassing the so-called neutron drip line, where neutrons begin to seep out of nuclei, the matter inside the neutron star crust undergoes a remarkable transformation. Instead of remaining as spherical atomic nuclei arranged in a crystal lattice, the protons and neutrons reshape into various non-spherical, energetically favorable structures. The density and pressure force competing interactions to settle on configurations that minimize the system's total energy, giving rise to these exotic geometrical phases. The shapes that emerge bear striking resemblance to types of pasta, hence the evocative naming: lasagna, spaghetti, gnocchi, and others. Essentially, these phases involve nuclear matter-forming sheets: lasagna, rods or filaments, spaghetti, spherical blobs, gnocchi, or even inverted forms resembling bubbles and tunnels. This variety arises because of a fine balance between the short-range strong nuclear force, which tends to bind nucleons together, and the long-range Coulomb repulsion among protons, which tries to push them apart. In the outer crust of the neutron star, nuclei crystallize into a solid lattice immersed in a sea of electrons. As we move inward beyond this region, the density climbs, and the spherical shape of nuclei becomes less stable. Nucleons rearrange to reduce the overall energy budget, creating these visually and conceptually striking forms. At these phases, matter is neither quite a liquid nor a solid, but exhibits characteristics of both: complex, frustrated structures resulting from competing forces. One of the remarkable implications of nuclear pasta is its influence on the star's macroscopic properties. For example, the irregular, complex shapes can scatter and trap neutrinos more efficiently than regular nuclear matter. Since neutrino emission is a primary cooling mechanism for neutron stars, the properties of nuclear pasta have significant consequences for how neutron stars lose heat and how rapidly they cool after their violent births. Moreover, nuclear pasta layers impact the neutron star's magnetic field and mechanical properties. The complicated geometry can create pinning sites for superfluid vortices and magnetic flux tubes, playing a critical role in phenomena such as pulsar glitches, sudden, irregular jumps in rotation speed detected in some neutron stars. The strength and elasticity of the pasta phases affect the crust's response to stresses, perhaps even influencing starquakes that can release bursts of X-rays and gamma rays. Studying nuclear pasta also poses substantial theoretical and computational challenges. The interactions are many-bodied and dominated by quantum forces that are difficult to reproduce experimentally. Scientists employ advanced numerical simulations, incorporating nuclear physics, condensed matter theory, and quantum many-body techniques to model these phases. Observationally, constraints on nuclear pasta come indirectly from thermal emissions, pulsar timing, and neutrino signals, since the star's crust is inaccessible to direct probing. In this way, nuclear pasta bridges microscopic nuclear physics with macroscopic astronomical behavior, highlighting how fundamental forces sculpt matter into exotic architectures that bear the imprints of their cosmic environment. Understanding these phases enriches our knowledge not only of neutron stars themselves, but of the behavior of dense nuclear matter, informing models that span from terrestrial nuclear experiments to high-energy astrophysics. As we continue our journey inward, this complex tapestry of matter under strain prepares us for even stranger possibilities nestled deeper within neutron stars' inner cores, where familiar particles may give way to exotic baryons and deconfined quarks. The landscape of dense matter is a continuum of mysteries, with nuclear pasta offering a vivid glimpse into the intricate complexity arising from nature's fundamental building blocks pressed to their limits. As we delve deeper into the heart of neutron stars, we enter a domain where matter is squeezed to densities so great that it may transcend the familiar particles that constitute ordinary nuclear matter. Beyond the neutrons and protons that dominate the star's composition, physicists theorize the emergence of exotic baryonic states, particles such as hyperons, which contain strange quarks, adding a new layer of complexity to the star's inner workings. This possibility opens a window onto strange matter, a form of matter that could fundamentally rewrite our understanding of neutron star cores and the behavior of matter under the most extreme conditions known in the universe. To grasp this concept, one must first appreciate what hyperons are. Hyperons are a family of baryons, like neutrons and protons, but distinguished by the inclusion of one or more strange quarks among their constituent quarks. Unlike up and down quarks that make up protons and neutrons, strange quarks imbue these particles with distinctive properties, including higher masses and altered interaction behaviors. Examples include the lambda, 129 and sigma, 3 hyperons. These particles are unstable under terrestrial conditions, rapidly decaying into lighter baryons. However, in the neutron star's core, the tremendous pressure and density may stabilize them, making their presence energetically favorable. Within neutron stars, the composition is governed by the principle of minimizing the system's energy under the balance of gravity and nuclear forces. As density rises beyond nuclear saturation density, the Fermi energy of neutrons escalates significantly. At some critical density, it becomes energetically advantageous for the system to convert some of the neutrons into hyperons, rather than forcing neutrons into ever higher momentum states. This conversion can reduce the star's pressure for a given density. Venturing deeper into the uncharted interiors of neutron stars, we encounter a profound question at the frontier of physics. Could the cores of these dense stellar remnants harbor free quark matter? Traditionally, matter as we know it is composed of atoms, which themselves consist of protons and neutrons confined tightly by the strong nuclear force. Protons and neutrons are made up of fundamental constituents called quarks, bound together so strongly that they never exist in isolation under normal conditions. However, under the intense pressures and densities found in neutron star cores, the boundaries confining quarks may dissolve, allowing quarks to roam freely, a phase known as quark deconfinement. Exploring this possibility bridges nuclear physics, quantum chromodynamics, QCD, astrophysics, and cosmology, setting the stage for revealing matter's behavior at nature's extremes. The concept of quark deconfinement arises from the theory of strong interactions, QCD, which dictates that quarks are ordinarily confined within hadrons, like protons and neutrons, by a property called color confinement. This confinement makes isolated quarks unobservable in everyday matter or even in laboratory nuclear physics experiments restricted to lower energies and densities. However, experiments with relativistic heavy ion collisions, such as those conducted at CERN's Large Hadron Collider, LHC, and Brookhaven's Relativistic Heavy Ion Collider, RHIC, have created fleeting states of deconfined quark-gluon plasma at high temperatures, briefly mimicking conditions prevalent microseconds after the Big Bang. Neutron star cores, while cold by cosmic standards, achieve densities surpassing several times nuclear saturation density, a realm not accessible in terrestrial laboratories through high-temperature plasmas, but rather through immense compression at comparatively lower temperatures. These conditions might facilitate a different route to deconfinement. Instead of heating quarks into plasma, crushing gravity may overcome the confining force thresholds, allowing quarks to exist unbound within a dense, degenerate medium, abruptly altering the star's internal composition and properties. If deconfinement occurs, the neutron star core may transition from a phase dominated by neutrons and protons to a quark matter phase, where up, down, and perhaps strange quarks move freely. This quark matter could take various forms, from a homogeneous quark-gluon plasma to more exotic phases such as color superconductors, where quarks pair via attractive color interactions, analogous yet profoundly distinct from electromagnetic superconductivity. Detecting the presence of such quark matter is a formidable challenge, as it leaves only subtle imprints on the star's macroscopic observables. For example, the equation of state, EOS, the relation between pressure and density within the star, is altered by the presence of exotic quark phases, affecting the star's mass-radius relationship. Stars containing quark matter cores might manifest smaller radii for a given mass, or exhibit distinctive cooling rates due to altered neutrino emission processes within the quark phase. Moreover, astrophysical events such as neutron star mergers are prospective laboratories for detecting quark deconfinement indirectly. The cryogenic titanic collisions produce transient hyperdense matter, and gravitational wave signals carry imprints of the EOS and internal composition. Recent observations of gravitational waves and electromagnetic counterparts offer preliminary constraints, tantalizing physicists with clues about the presence of quark matter, but stopping short of definitive proof. Theoretically, models vary from those with sharp first-order phase transitions leading to distinct quark cores to scenarios where hadronic and quark matter phases smoothly blend, forming mixed phases or pasta-like structures in the deep core. These models affect stability criteria and maximum mass thresholds for neutron stars, intertwining with puzzles such as explaining neutron stars with unexpectedly high masses above 2 solar masses. In the quest to probe quark deconfinement, researchers also rely on nuclear physics experiments and lattice QCD simulations to refine predictions, hoping to map the dense matter phase diagram. However, the low-temperature, high-density corner of this diagram remains among the most enigmatic and mathematically intricate regions in physics. Ultimately, whether neutron star cores truly contain free quark matter remains an open and captivating mystery. The answer promises to unlock fundamental insights about the strong force, the phases of matter under extreme conditions, and the life cycle of stars, bridging the smallest scales of particle physics with vast cosmic phenomena. As we probe this frontier, the universe invites us to rethink the very fabric of matter in the extraordinary hearts of neutron stars. Venturing into the deepest frontiers of theoretical astrophysics, we encounter a captivating possibility that challenges traditional conceptions of neutron stars altogether: the existence of strange quark stars. These hypothetical stellar remnants are composed predominantly, or even entirely, of strange quark matter, a form of matter that transcends conventional nuclear constituents and may represent a true ground state of matter under extreme conditions. Exploring strange quark stars opens a window into profound questions about the nature of matter, the limits of stellar stability, and the very fabric of the cosmos. But what exactly is strange quark matter? To understand this, we must first return to the notion of quark deconfinement, where protons and neutrons dissolve into their fundamental quark constituents: up, down, and strange quarks. Strange quark matter theorizes that at sufficiently high densities, a bulk phase of deconfined quarks containing comparable numbers of up, down, and strange quarks may form a thermodynamically stable or metastable matter phase. This idea emerged from theoretical studies suggesting that the inclusion of strange quarks lowers the system's energy per baryon, making strange quark matter potentially more stable than ordinary nuclear matter. Unlike neutron stars, which contain a crust of nuclei enveloping denser nuclear matter, strange quark stars might lack a traditional nuclear crust or have a very thin outer layer. Their interiors would be a quark-gluon plasma in a color superconducting state, featuring paired quarks in novel quantum phases. These quark stars would be incredibly compact. For a given mass, their radius could be smaller than that of neutron stars, altering observational signatures such as gravitational redshift and thermal emission patterns. Key theoretical models propose various forms of strange quark stars, including bare quark stars with exposed quark surfaces and hybrid stars where strange quark matter cores coexist with hadronic outer layers. Each type offers distinct predictions about mass-radius relations, cooling rates, magnetic field structures, and rotational dynamics. For example, strange quark stars may cool more rapidly due to enhanced neutrino emission mechanisms intrinsic to quark matter, which could help explain observations of unusually cold neutron stars. The implications of confirming strange quark stars are sweeping. On a fundamental physics level, their existence would validate predictions from quantum chromodynamics in regimes unattainable by terrestrial experiments and support the strange matter hypothesis. This would redefine the classification of compact stars and provide natural laboratories to study color superconductivity, quark pairing mechanisms, and the behavior of dense cold quark matter. Astrophysically, strange quark stars could explain certain observational enigmas, such as some compact stellar objects whose inferred masses and radii are challenging to reconcile with standard neutron star models. They might also influence gravitational wave signals from neutron star mergers if one or both progenitors contain strange quark matter, potentially affecting merger dynamics, ejecta composition, and electromagnetic counterparts, thereby shaping heavy element nucleosynthesis scenarios. Detection and confirmation remain formidable challenges. Since strange quark stars and neutron stars can be similar in mass and radii, distinguishing them requires precise observations of starquakes, spin glitches, thermal spectra, and especially gravitational wave signatures, which encode the star's internal equation of state. Future advances in multi-messenger astronomy, with synergistic observations from gravitational wave detectors, high-energy telescopes, and neutrino observatories, will be critical in testing these exotic theoretical candidates. In essence, strange quark stars offer a tantalizing theoretical landscape where the boundaries of matter are pushed to extremes and new forms emerge from the fundamental symmetries and interactions of the quantum world. They challenge our understanding of compact objects and invite us to consider that the universe may be home to stellar bodies far stranger and more wonderful than previously imagined. As we continue, we will explore even more intricate quantum phenomena predicted in these extreme environments, such as the mysterious color superconductivity and color flavor locking phases, exotic states which could dominate the behavior of quark matter, further revealing the rich tapestry of physics awaiting discovery within the hearts of the densest stars. Diving deeper into the exotic realms of quark matter within neutron star cores, we encounter a fascinating and complex quantum phenomenon known as color superconductivity. This state, predicted by the theory of quantum chromodynamics, QCD, fundamentally transforms how quarks, the elementary constituents of protons and neutrons, interact under extreme conditions. More intriguingly, it can lead to a peculiar and elegant phase called color flavor locking, where the distinctions between quark colors and flavors intertwine to produce a unique form of quantum order. To unravel this mystery, we must first understand the underlying physics and its astonishing implications for neutron star interiors. Color superconductivity arises because quarks, like electrons in ordinary superconductors, can form pairs at sufficiently low temperatures and high densities. While electrons pair via electromagnetic interactions, quark pairing is governed by the strong force mediated by gluons, the carriers of the color charge in QCD. When quarks pair, they condense into a collective ground state that enables them to move without resistance, akin to the flow of electric current in a superconductor, but here involving color charge rather than electric charge. The analogy to familiar superconductivity helps visualize the concept, yet color superconductivity is far richer due to the added complexity. Quarks come in 3 colors: red, green, blue, and multiple flavors: up, down, strange, and potentially heavier ones. At the extreme densities in neutron star cores, quarks' Fermi surfaces become degenerate, and their interaction energies favor the formation of different pairing patterns depending on density and composition. Among the most remarkable predicted phases is color flavor locking, CFL, where the quark pairs lock their color and flavor symmetries together. This means that a red up quark pairs with a green down quark, a green up quark pairs with a blue strange quark, and so on, weaving a highly symmetric and tightly integrated quantum state. In the CFL phase, color and flavor symmetries are broken in a way that all quark excitations gain energy gaps, suppressing dissipative processes and creating a perfect superfluid and superconductor with unique properties. This color-flavor locked matter would be electrically neutral without the need for electrons, influencing the neutrino emissivity and thermal evolution of neutron stars. Such properties could profoundly affect cooling rates and magnetic field characteristics, potentially leaving observable imprints in astrophysical data. However, the precise conditions under which the CFL phase or other color superconducting phases emerge remain a frontier topic. Factors such as quark masses, the presence of strange quarks, and the overall density determine the favored phase. Additionally, transitions between phases may occur as density changes from the star's outer regions inward, possibly resulting in mixed or crystalline superconducting phases with complex spatial patterns. Understanding color superconductivity is challenging due to the non-perturbative nature of strong interactions at these densities, limiting direct computational approaches. Nonetheless, theoretical advances using effective models and lattice QCD simulations, combined with astrophysical constraints gleaned from neutron star observations, continue to shed light on these enigmatic states. The possibility that such exotic quantum states exist in nature within neutron star cores represents a profound intersection of particle physics and astrophysics, offering a glimpse into matter under the most extreme conditions. Color superconductivity and color flavor locking not only deepen our understanding of fundamental forces, but also enrich the narrative of how neutron stars sustain their structure and evolve over cosmic timescales. As we continue to unravel these mysteries, we will soon turn our attention to the guiding principles governing the structure of these stars, how the Pauli exclusion principle under pressure dictates the arrangement and behavior of fermions, shaping the neutron star's remarkable equilibrium and observable characteristics. At the heart of a neutron star's remarkable stability lies a fundamental principle rooted deep in the quantum fabric of the universe, the Pauli exclusion principle. This cornerstone of quantum mechanics asserts that no two identical fermions, particles with half-integer spin, can occupy the same quantum state simultaneously. In the incredibly dense environment of a neutron star, it is this principle that fundamentally dictates the star's structure, providing the essential pressure to counterbalance the crushing grip of gravity and enabling a delicate equilibrium in the cosmos. To understand the profound influence of the Pauli exclusion principle on neutron stars, we first need to appreciate what fermions are. The primary fermions relevant here are neutrons, protons, and electrons, each bearing half-integer spin, 1.2. Throughout the star, these particles fill available quantum states, beginning with the lowest energy levels and progressing upwards. But since the exclusion principle forbids any two identical fermions from sharing the exact same quantum state, at high densities, the particles crowd into higher and higher momentum states, increasing the system's overall pressure even at zero temperature. This pressure is known as degeneracy pressure. In the dense core of a neutron star, degeneracy pressure is predominantly due to neutrons, hence the term neutron degeneracy pressure. As gravity compresses the matter beyond nuclear densities, neutrons are packed so tightly that they can't be squeezed closer without forcing them into already occupied quantum states. The resulting quantum pressure from this packed arrangement resists further compression, creating a quantum mechanical counterforce that halts gravitational collapse, provided the star's mass isn't too great. Electrons and protons also contribute to degeneracy pressure, especially in the less dense crustal regions. But as neutron stars evolve and matter undergoes neutronization, neutrons dominate. The interplay of particle species and their respective degeneracy pressures sculpt the internal profiles of density, pressure, and composition within the star. The equation of state, a functional relationship expressing pressure as a function of density and temperature, results from these quantum mechanical considerations in concert with nuclear interaction forces. Yet, degeneracy pressure is not the only quantum effect dictating the microphysics. Nuclear forces come into play at these densities, modifying how fermions interact and affecting the stiffness or softness of the equation of state. Despite their complexities, the unyielding foundation of the Pauli exclusion principle remains central. It is the reason matter resists complete collapse, a cosmic quantum safeguard. This principle also intimately governs neutron star phenomena observable from Earth. For instance, the star's maximum stable mass, the Tolman-Oppenheimer-Volkoff limit, arises because beyond a critical mass, degeneracy pressure and nuclear repulsion can no longer withstand gravity, forcing catastrophic collapse to a black hole. Conversely, the principle explains pulsar glitches, sudden irregularities in rotation caused by interactions in the neutron superfluid, where vortices are pinned because fermions cannot occupy forbidden states and therefore behave in quantized manners. Moreover, the Pauli exclusion principle determines the neutron star's temperature evolution and chemical composition. It limits how matter can rearrange during cooling and cooling rates, influencing neutrino emission processes and thermal properties at macroscopic scales. The subtle yet powerful quantum choreography of fermions under pressure is thus woven into every aspect of neutron star evolution and behavior. Visualizing this quantum principle's cosmic effect is challenging, as it operates on scales vastly removed from human intuition. Yet, it is awe-inspiring to consider that the seemingly abstract rule governing tiny particles dictates the very architecture of some of the universe's densest visible objects. The Pauli exclusion principle is a testament to nature's intricacy, showing how microphysical laws govern grand celestial phenomena. As we continue to explore neutron stars, it becomes clear that the cosmic dance between quantum mechanics and gravity is delicate and intricate. The Pauli exclusion principle stands as a fundamental pillar in this interplay, shaping neutron star structure, defining limits to stability, and guiding their observable traits. Following this, our journey will steer towards how astronomers and physicists attempt to observe and unlock the secrets of neutron stars using pulsar timing, gravitational waves, and X-ray emissions. Windows into these quantum giants' exotic realms. Observing a neutron star is akin to peering through a dense veil into one of the universe's most extreme laboratories, where matter exists under conditions unreplicable on Earth. Despite their compact size, typically just about 20 kilometers across, neutron stars are prolific emitters of signals across the electromagnetic spectrum, and their rapid, precise rotations serve as cosmic clocks with incredible regularity. Today, 3 observational techniques stand at the forefront of probing neutron star interiors and revealing their fundamental nature: pulsar timing, gravitational wave detection, and X-ray emission analysis. Together, these methods provide a multifaceted window into the enigmatic physics of neutron stars. Pulsars are rapidly rotating neutron stars that emit tightly beamed radiation, often in radio frequencies, sweeping across Earth at precise intervals as their magnetic poles rotate into and out of view. Pulsar timing, the careful measurement of these arrival times, has historically revolutionized astrophysics, beginning with the discovery of the first pulsar in 1967. Because pulsars act like extremely stable celestial clocks, even tiny changes in their rotation periods can be detected with exceptional precision. These subtle timing irregularities can reveal mysteries about neutron star interiors, such as glitches, sudden speed-ups attributed to the dynamics of superfluid vortices in the crust or core. Analyzing glitches gives us rare clues about the otherwise inaccessible internal superfluid layers, magnetic field evolution, and the coupling dynamics between the crust and the liquid interior. Moreover, timing arrays of millisecond pulsars have become invaluable in detecting the subtle background of gravitational waves from supermassive black hole binaries, showcasing the cross-disciplinary impact of pulsar timing. Gravitational waves, ripples in the fabric of spacetime predicted by Einstein's general relativity, offer a novel, powerful way to probe neutron star interiors. The landmark detection in 2017 of gravitational waves from a binary neutron star merger, GW170017, by the LIGO and Virgo observatories opened a new era of multi-messenger astronomy. The waveform and amplitude of these gravitational waves encode vital information about the neutron star's masses, spins, and most intriguingly, their internal equations of state. As 2 neutron stars spiral closer, tidal distortions occur. Their deformability depends on internal pressure and density distributions. By analyzing gravitational wave signals with incredible precision, astrophysicists extract constraints on the dense matter EOS, helping distinguish between competing nuclear and exotic matter models, including the presence of quark matter or hyperons. Moreover, gravitational waves complement electromagnetic signals, such as short gamma-ray bursts and kilonova emissions, providing a more holistic view of the merger processes and the nature of ultra-dense matter. X-ray emissions from isolated neutron stars or accreting binaries form another critical observational pillar. The gravitational field near a neutron star's surface is so intense that it impacts photon energy as observed on Earth, thereby encoding clues about the star's compactness. Space telescopes like NASA's NICER mission on the International Space Station specialize in high-precision X-ray timing and spectroscopy, enabling the measurement of mass and radius with unprecedented accuracy. These measurements refine the neutron star EOS by linking spectral data to surface area and gravitational redshift. Additionally, hotspots on neutron star surfaces caused by magnetic field funneling or accretion rotate in and out of view, producing characteristic X-ray pulsations. Analysis of these pulsations, including their waveforms and spectral evolution, further constrains the star's shape, rotational dynamics, and magnetic field geometry. Observations of transient X-ray bursts resulting from thermonuclear explosions on neutron star surfaces provide insights into accretion processes, nuclear burning under extreme gravity, and the composition of neutron star envelopes. Combining these observational channels, radio timing, gravitational waves, X-rays, ushers in a new era of precision neutron star astrophysics. Their synergy allows scientists to cross-validate models and delve into the interplay of gravity, quantum mechanics, nuclear physics, and electromagnetism within these compact objects. Yet many mysteries remain. For instance, precisely mapping dense matter's EOS, understanding phase transitions in the core, and detailing neutron star magnetic field evolution are open challenges. Future instruments such as next-generation gravitational wave detectors, advanced X-ray observatories, and expanded radio telescope arrays promise to deliver revolutionary data illuminating neutron star interiors with unprecedented clarity. In essence, these observation techniques act as cosmic stethoscopes, allowing humanity to listen to the faint but rich voices of neutron stars and decode their internal secrets. By precisely measuring pulsar spins, catching ripples of spacetime, and decoding high-energy photons, we forge a more complete understanding of these extreme astrophysical laboratories, unveiling the hidden physics governing the densest matter in the observable universe. As we move from observational discoveries to theoretical advancements, the knowledge gained here will ripple outward, reshaping both fundamental physics and our view of the cosmos. At the intersection of cosmic violence and the birth of the universe's heaviest elements lies one of the most dynamic areas of modern astrophysical research: neutron star mergers. These colossal collisions between two neutron stars represent astrophysical cataclysms of immense power and profound significance, reshaping matter and energy on scales that both challenge and enrich our understanding of the cosmos. Recent advances in observational astronomy, gravitational wave detection, and theoretical modeling have brought new clarity to this spectacular phenomenon and unveiled its pivotal role in nucleosynthesis, the creation of heavy elements essential to planetary systems and life itself. Neutron star mergers occur in binary systems where two neutron stars, locked in mutual gravitational dance, gradually spiral inward over millions to billions of years as their orbits decay through emission of gravitational radiation. Eventually, their spheres of ultra-dense matter collide and merge in a cataclysmic event detectable across multiple messengers: gravitational waves, high-energy electromagnetic emissions, and streams of subatomic particles. The landmark detection of gravitational waves from such a merger, named GW7817 by LIGO and Virgo in 2017, combined with an extensive follow-up of electromagnetic signals, revolutionized our understanding of these cosmic collisions. One of the most exciting revelations from this event was how neutron star mergers serve as cosmic foundries for heavy elements beyond iron that populate the periodic table. The extreme conditions present during and after the merger provide an environment ripe for rapid neutron capture, known as the R process. In this process, atomic nuclei rapidly absorb neutrons, creating highly unstable isotopes that then decay into stable, heavy nuclei, such as gold, platinum, uranium, and many others. Until recently, the astrophysical origins of these elements were debated, with supernovae considered possible sites, but often insufficient to fully explain observed abundances. Neutron star mergers have now emerged as a primary site, supported by spectral observations of kilonova light that bear the unmistakable signatures of freshly synthesized R process elements. The ejecta expelled during these mergers, a mixture of neutron-rich matter thrown off in tidal tails and winds from the remnant, cools and radiates, producing a distinctive glow across optical, infrared, and ultraviolet wavelengths. Careful analysis of these emissions provides a window into the mass, speed, and composition of the expelled material, offering constraints on the physical conditions and nuclear reactions occurring. This multidisciplinary approach blends nuclear physics, astrophysics, and observational astronomy to refine models of heavy element production. Furthermore, neutron star mergers bear directly on the physics of neutron star interiors and the equation of state of dense matter. The gravitational waveforms carry imprints of how deformable and compressible the stars are before collision, while the mass and composition of merger remnants inform us about maximum neutron star masses and the possible formation of black holes. Some recent studies indicate that remnant hypermassive neutron stars survive briefly post-merger before collapsing, allowing new insights into matter under even more extreme density and temperature conditions. These breakthroughs have also invigorated a new era of multi-messenger astronomy, where coordinating observations across gravitational waves, electromagnetic radiation, and neutrinos aims to uncover the complex physics of neutron star mergers comprehensively. Future observatories promise improved sensitivity and resolution, enabling us to map merger rates across cosmic history, probe the distribution of heavy elements in galaxies, and explore connections to phenomena like short gamma-ray bursts. In summary, the latest research into neutron star mergers reveals a dramatic cosmic alchemy, wherein the densest stars collide, sending ripples through space-time and seeding the universe with the very building blocks of planets and life. These events not only deepen our understanding of fundamental physics, gravity, nuclear reactions, and dense matter equations of state, but also weave a grand narrative linking the death throes of stars to the elemental diversity that shapes our existence. As observational and theoretical techniques advance in tandem, neutron star mergers will continue to illuminate fundamental astrophysical questions at the cutting edge of human knowledge. Understanding the fundamental nature of neutron stars hinges critically on precise measurements of two key observable properties: mass and radius. These parameters serve as essential probes into the dense matter equation of state, EOS, the relationship between pressure, density, and temperature that dictates how matter behaves under the extreme conditions within neutron star interiors. Over the past decades, astrophysicists have refined a variety of observational and modeling techniques to measure neutron star masses and radii with increasing accuracy, thereby placing stringent constraints on the EOS and narrowing down theoretical models that describe ultra-dense matter. The mass of neutron stars can often be determined with remarkable precision through the study of binary systems. When a neutron star is paired with a companion star, whether another neutron star, white dwarf, or main sequence star, careful timing of orbital motions and application of Keplerian dynamics allow astronomers to calculate the pulsar's mass. Radio telescopes measure pulse arrival times to microsecond precision, enabling detailed orbital parameter estimation. The discovery of neutron stars with masses near or above two solar masses, such as PSR J0348 plus 0432 and PSR J0740 plus 66620, has imposed strong lower limits on the maximum allowable mass, indicating that matter inside must be sufficiently stiff to avoid collapse into a black hole. This challenges softer EOS models and those that predict exotic, softening phases at high densities. Determining neutron star radii proves more challenging, as the star's small size demands indirect inference from electromagnetic emissions and modeling. Techniques include analyzing thermal X-ray emissions from isolated neutron stars or accretion-heated surfaces in X-ray binaries, where the observed spectrum and flux, corrected for distance and interstellar absorption, provide clues about the emitting area and thus radius. More recently, observations from NASA's NICER mission have offered transformative insights by combining precise X-ray timing and spectroscopy to map surface hotspots, allowing simultaneous constraints on mass and radius through modeling of relativistic light bending near the neutron star surface. These measurements help discriminate among competing EOS predictions by revealing how compressible neutron star matter is under gravity. Both mass and radius measurements together define the neutron star mass-radius relation, a crucial diagnostic trait that encodes the EOS. A stiffer EOS leads to larger radii for a given mass, while softer EOSs predict more compact stars. By compiling data from multiple sources and employing Bayesian inference techniques, researchers can infer probability distributions of the EOS parameters, effectively pushing the theoretical models toward those compatible with observed measurements. Furthermore, gravitational wave observations of neutron star mergers, as first achieved through the GBUB 70817 event, enrich this mass-radius constraint framework. The tidal deformability signal embedded in gravitational waveforms depends sensitively on the EOS, enabling complementary constraints that cross-validate and refine radii and maximum mass estimates. The combined analysis of electromagnetic signals, pulsar timing, and gravitational wave data forms a powerful multi-messenger toolkit for EOS exploration. However, challenges persist. Systematic uncertainties such as precise distance measurements, assumptions about neutron star atmospheres or surface compositions, and statistical limitations of observed samples continue to affect radius determinations. Moreover, theoretical degeneracies mean that multiple EOS models can fit currently available data, leaving open questions about the detailed microphysics of matter at supranuclear densities. Nevertheless, continuous advancements in observations, from improved telescope sensitivity, larger pulsar timing arrays, to future gravitational wave detectors, promise steadily refined constraints. Laboratory nuclear experiments, probing neutron-rich matter, and sophisticated theoretical simulations further enhance interpretative power. Together, these efforts are narrowing the viable EOS parameter space, bringing us closer to decoding the true nature of matter at the heart of neutron stars. In summary, precise mass and radius measurements are pivotal in confronting dense matter theory with reality, enabling scientists to push the boundaries of the EOS and deepen our understanding of matter under the universe's most extreme conditions. This endeavor channels the interplay of astrophysics, nuclear physics, and fundamental theory, forming a critical chapter in our quest to unravel the mysteries hidden within neutron star cores. In the quest to understand the profound mysteries of neutron star cores, scientists recognize that direct observation alone, the light, neutrinos, or gravitational waves reaching Earth, is insufficient to fully unravel the complex physics at play under such extreme states. To complement these glimpses from afar, physicists have turned to terrestrial laboratories, and cutting-edge particle accelerators, seeking to create and study conditions analogous to those in a neutron star's core. Though it is impossible to replicate the exact density and pressure of a neutron star, lab experiments delve into related regimes of nuclear matter under extreme temperatures and densities, pushing the boundaries of physics and enabling us to constrain the properties of matter under extreme compression. One of the primary techniques involves high-energy heavy ion collisions, in which nuclei of large atoms like gold or lead are accelerated to near light speeds and slammed into each other. Facilities such as the Relativistic Heavy Ion Collider, RHIC, at Brookhaven National Laboratory and the Large Hadron Collider, LHC, at CERN have pioneered this approach. When these heavy ions collide, they briefly generate conditions of extraordinarily high temperature and density, creating a fleeting state known as the quark-gluon plasma, QGP, where quarks and gluons, the fundamental constituents of protons and neutrons, are liberated from confinement. Though these temperatures exceed those in neutron star cores, and the created matter exists only for fractions of a second, studying the QGP provides crucial insight into the fundamental interactions governed by quantum chromodynamics, QCD, associated phase transitions, and transport properties of strongly interacting matter. Complementing these high-temperature experiments, efforts are underway to explore dense, cold nuclear matter more akin to that inside neutron stars. Upcoming and planned facilities, such as the Facility for Antiproton and Ion Research, FAIR, in Germany, and the Nucleotron-based Ion Collider Facility, NICA, in Russia, aim to collide heavy ions at lower energies, increasing the baryon density of the system to approach somewhat comparable conditions. These experiments help scientists investigate how hadronic matter behaves when compressed, possibly enabling glimpses of phase transitions anticipated in neutron star cores, like the onset of hyperons or quark deconfinement. Beyond ion collisions, precision measurements of nuclear properties and reactions provide valuable constraints on the nuclear equation of state under neutron-rich conditions that simulate neutron star matter. Isotopes with extreme neutron excess are synthesized and studied at rare isotope facilities, such as the Facility for Rare Isotope Beams, FRIB, in the United States. Reaction cross-sections, masses, and decay modes of these exotic nuclei hone models of nuclear forces relevant for neutron-rich matter. Observations of phenomena like neutron skin thickness and collective excitations directly impact our understanding of symmetry energy, a critical component of the equation of state-governing neutron star structure. In addition, advances in nuclear theory, supported by data from experiments, enable sophisticated modeling of dense matter. Lattice QCD simulations, ab initio nuclear calculations, and effective field theories help predict matter behavior at high densities, refine particle interactions, and explore possible exotic states such as color superconductivity and strange matter. While computational and theoretical challenges persist, these efforts synergize with laboratory data and astrophysical observations to build a comprehensive picture. Laboratory research also facilitates exploration of phenomena linked to neutrino physics and weak interactions, essential for neutron star cooling and evolution. Studies of beta decay and neutrino scattering provide critical inputs for understanding neutrino opacities and roles within dense matter environments. Though laboratory recreations of neutron star core conditions remain limited by scale and transient times, the advances in high energy and nuclear physics have transformed our understanding of dense matter physics. Bridging the cosmic and the terrestrial, these experiments empower astrophysicists to calibrate models, validate theoretical predictions, and interpret signals from distant neutron stars with greater confidence. Looking ahead, emerging facilities and experimental techniques promise to narrow the gap between Earth-bound experiments and neutron star interiors. By continuing this dialogue between laboratory science and astrophysical phenomena, humanity moves steadily closer to decoding the profound secrets locked within the densest observable matter in the universe. One of the most captivating puzzles in neutron star physics centers on the existence of higher-mass neutron stars, those tipping the scales at or beyond about 2 solar masses. These massive remnants push the boundaries of known physics, challenging theoretical models of dense matter and prompting profound questions about the nature of the equation of state, EOS, the ultimate composition of neutron star cores, and the limits to stellar stability. Interpreting observational data from these hefty neutron stars is essential to advancing our understanding, but it is also complex and highly nuanced, involving a careful dance between astrophysical measurements, nuclear physics, and fundamental theory. Historically, neutron stars were expected to have typical masses close to 1.4 times that of the Sun, clustered tightly within a narrow range. This expectation stemmed from observations in binary systems and supernova theory. However, precision pulsar timing and other methods have revealed neutron stars with significantly higher masses. For instance, PSR J1994 223 measured at about 1.97 solar masses, and more recently, PSR J0740+X620, reaching around 2.1 solar masses. Such discoveries demand that the EOS describing neutron star interiors must be sufficiently stiff, that is, able to produce enough pressure at high density to prevent collapse under gravity, thereby excluding softer EOS models that predict lower maximum masses. These higher masses present a multifaceted interpretive challenge. On one hand, supporting such large masses suggests that the internal composition is dominated by strongly interacting nucleons and potentially exotic particles whose interactions produce significant pressure. On the other hand, theoretical models incorporating exotic phases, hyperons, Bose condensates, or deconfined quark matter generally soften the EOS, lowering the maximum possible mass and sometimes contradicting observations of massive stars. Reconciling these seemingly conflicting constraints has propelled researchers to refine nuclear interaction models, consider novel particle interactions, and explore hybrid star configurations with layered phases. Interpreting mass measurements also involves understanding observational uncertainties and selection biases. Precise mass determination relies heavily on pulsar timing in binary systems, but often with assumptions about system inclination, companion masses, or orbital dynamics. Lasting confidence emerges from independent and consistent measurements across multiple systems, bolstered by gravitational wave observations, where waveform analysis constrains component masses and their distributions. Additionally, radius measurements intersect with the mass puzzle. The combination of large mass and small radius candidates demands an EOS, allowing such compactness without collapse. Variability in radius estimates, amplified by differences in modeling neutron star atmospheres and surface emissions, complicates clear-cut conclusions. As yet, no definitive radius measurement fully resolves these ambiguities, keeping interpretations of mass radius data as an active area of research. Further intricacies arise from recent gravitational wave detections of neutron star mergers. These events offer dynamic probes into mass distributions, tidal deformabilities, and merger remnant properties. They suggest limits on maximum masses and hint at the possibility that the remnant's collapse into a black hole may be delayed or prompt, depending on the EOS and stellar masses involved. These observations integrate into the broader puzzle, providing fresh constraints and raising new questions about the behavior of ultra-dense matter under rapid dynamical changes. Moreover, higher-mass neutron stars intersect with questions about their formation and evolution. How such massive neutron stars arise through accretion, mergers, or direct supernova collapse, might influence internal composition and thermal history, which in turn affects on measurable features such as rotational behavior and cooling rates. Understanding evolutionary paths adds further depth and complexity to data interpretation. In conclusion, the puzzle of higher-mass neutron stars offers a thrilling confluence of observation and theory. Interpreting their data requires synthesizing multiple lines of evidence, from pulse timing, X-ray spectral analysis, gravitational wave signals, and nuclear physics, to refine models of dense matter. The balance between stiff and soft EOS models remains delicate, and the implications of these stars ripple across astrophysics and fundamental physics alike. As observations become increasingly precise and theoretical frameworks evolve, this puzzle will continue to drive progress in unraveling the deepest secrets of neutron star interiors and the fundamental properties of matter in the universe's most extreme crucibles. At the very core of neutron star physics lies a profound enigma, one that has mystified scientists for decades. What is the maximum mass a neutron star can possess before it succumbs to gravity's inexorable pull and collapses into a black hole? And what is the ultimate fate of matter beyond this threshold? These open questions stand at the frontier of astrophysics, intertwining the laws of quantum mechanics, nuclear physics, general relativity, and even speculative theories beyond our current understanding. Exploring them requires delving into the delicate balancing act of forces that sustain these compact objects and contemplating the dramatic transitions that occur when these balances are disrupted. The concept of a maximum mass limit stems from the competing influences within a neutron star. Gravity relentlessly strives to compress the star's enormous mass into an ever smaller volume, while quantum mechanical degeneracy pressure, principally from neutrons, along with nuclear repulsive forces and other exotic factors, resist collapse. This equilibrium is not limitless. Theorists have long calculated an upper bound known as the Tolman-Oppenheimer-Volkoff (TOV) limit, often estimated to lie between approximately 2 to 3 times the mass of the Sun. However, the precise value remains uncertain, largely due to the unresolved nature of the equation of state, EOS, governing ultra-dense matter. Determining this maximum mass is not merely an academic exercise. It has deep astrophysical ramifications. For instance, the observed masses of the heaviest neutron stars, pulsars measuring around 2 solar masses, already push the boundaries of many EOS models. If the EOS is too soft, the degeneracy pressure cannot support such masses, indicating that more complex forms of matter or stiffening mechanisms are at play. Conversely, an overly stiff EOS could allow neutron stars to sustain higher masses, modulating expectations for the frequency and nature of black hole formation. Beyond this threshold, gravitational collapse is thought to be inevitable, yet what precisely transpires remains an active field of research. The neutron star may undergo a catastrophic collapse into a black hole, a region of spacetime from which not even light can escape. Alternatively, transient exotic states, such as hypermassive neutron stars or quark stars, might form temporarily, supported by differential rotation, thermal pressure, or exotic particle interactions, before eventual collapse or stabilization. The physics governing these transitions criticize our foundational theories. For example, the interplay between quantum mechanics and general relativity becomes especially salient, suggesting that new physics, perhaps rooted in quantum gravity, could influence outcomes. Some speculative models even contemplate the possibility of, at the frontier where neutron stars cease to exist and black holes emerge, we confront the profound interplay between gravity, quantum mechanics, and the fundamental nature of spacetime itself. This realm, where densities surpass the capabilities of our most mature theories, beckons the enigmatic domain of quantum gravity, a theoretical framework yet to be fully realized that seeks to unify Einstein's general relativity with the principles of quantum mechanics. Exploring this threshold offers glimpses of possible surprises that could reshape our understanding of black holes, neutron stars, and the cosmos. General relativity elegantly describes gravitation as the curvature of space-time, caused by mass and energy, predicting phenomena like black holes where gravity becomes so intense that not even light escapes. Quantum mechanics governs the non-intuitive behavior of particles at the smallest scales. Yet, these frameworks stand largely incompatible when attempting to describe conditions at the singularities inside black holes or the ultra-dense cores beyond neutron star stability. One compelling question is, what truly happens as a neutron star collapses at or beyond the Tolman-Oppenheimer-Volkoff limit? Classical theory foresees the formation of a singularity, an infinitely dense point where known physics breaks down. Quantum gravity aims to resolve or reinterpret this singularity, possibly predicting novel phases of matter or space-time structure. Leading approaches to quantum gravity, such as string theory or loop quantum gravity, suggest various outcomes. For example, loop quantum gravity posits that space-time is quantized, potentially preventing true singularities through a bounce or phase transition, implying a finite density core or exotic compact objects. String theory, with its vibrational modes and extra dimensions, hints at modified black hole structures or particles that could emerge under extreme conditions. Beyond the classical black hole horizon, theoretical speculation entertains exotic compact objects that mimic black holes' gross features yet differ internally, such as gravastars, boson stars, or fuzzballs in string theory. These objects challenge the very notion of event horizons and information paradoxes, offering potential resolutions to long-standing puzzles about how information is preserved in gravitational collapse. Moreover, quantum effects near black hole horizons, like Hawking radiation, introduce thermodynamic properties to black holes, linking gravity, quantum mechanics, and statistical physics. Such phenomena underscore the subtle and rich physics that may emerge near and beyond the neutron star maximum mass threshold. In addition, new physics, such as modifications to gravity, extra spatial dimensions, or novel particle interactions, could come into play at these scales. Observations of neutron stars near the maximum mass, gravitational wave signatures of mergers, and high-precision pulsar timing provide empirical constraints, gradually informing or challenging these theoretical speculations. In essence, the black hole threshold is more than a simple mass boundary. It is a gateway to unexplored physics where quantum gravity effects become indispensable. The surprises awaiting discovery here promise to deepen our grasp of the universe's fundamental workings, inspiring both experimental inquiry and theoretical innovation. As we transition from speculation to implications, we recognize that unraveling these mysteries impacts cosmology, the structure of matter, and the very origin and fate of the cosmos. A testament to human curiosity propelling us ever forward into the depths of the unknown. Neutron stars are not simply remnants of massive stellar deaths. They are fundamental cornerstones in our broader understanding of the cosmos and the very structure of matter. The extreme conditions within neutron stars, densities surpassing atomic nuclei, and gravitational fields distorting spacetime itself, serve as natural laboratories probing physics that shapes the universe on both the largest and smallest scales. Consequently, the study of neutron star cores ripples through cosmology and particle physics, unveiling insights into the universe's evolution, elemental synthesis, and the fundamental forces governing matter. One significant implication lies in cosmology's narrative of how the universe formed and evolved. Neutron stars provide direct evidence for the endpoint of stellar evolution, enriching the interstellar medium through supernova explosions that seed the cosmos with heavy elements. The synthesis of elements heavier than iron, long theorized to largely occur during these cataclysmic events, and the subsequent neutron-star mergers, plays a pivotal role in cosmic chemical evolution. These heavy elements, gold, platinum, uranium, are forged via rapid neutron capture processes, the R process, under the extreme conditions present during mergers. Thus, by studying neutron stars and their collisions, we gain a clearer picture of the origin of the periodic table's heaviest constituents, directly tying stellar remnants to the material basis of rocky planets and, ultimately, life itself. On a grander scale, neutron stars and their mergers influence the history of galaxy formation. The energetic feedback from supernovae shapes star formation rates by injecting kinetic energy and enriching galactic gas, while merger events distribute newly synthesized elements, thus regulating cosmic chemical heterogeneity. Moreover, as sources of gravitational waves, neutron-star mergers open a new window into the universe's expansion rate and the properties of dark energy, a mysterious force accelerating cosmic expansion. By analyzing gravitational wave signals alongside electromagnetic counterparts, scientists can independently measure distances and redshifts, refining cosmological parameters. Beyond astrophysics, neutron stars challenge and inform our understanding of matter's fundamental architecture. The exotic phases hypothesized in their cores, hyperons, deconfined quarks, color superconductivity, extend the boundaries of known particle physics. These states probe quantum chromodynamics under conditions unattainable on Earth, potentially revealing new symmetries, particle interactions, and phases of matter. Discovering and characterizing these forms impacts the standard model of particle physics, offering avenues to resolve outstanding puzzles such as the nature of dark matter or the behavior of fundamental forces at extreme densities. Furthermore, neutron stars exemplify the interplay between gravity and quantum mechanics, bridging gaps toward a unified theory of quantum gravity. Their interiors may harbor clues to novel physics that reconcile the curvature of spacetime with quantum uncertainties, influencing theories about black holes, spacetime singularities, and the early universe. Collectively, the implications of neutron star research cascade from the microcosm of subatomic particles to the macrocosm of galactic evolution and cosmic structure. They embody a nexus where astrophysics, cosmology, and fundamental physics converge, reminding us that understanding these dense stellar remnants is inextricably tied to comprehending our universe's past, present, and future. As our curiosity persists, driven by advancing technology and theoretical insights, decoding neutron star cores not only quells profound scientific questions, but also enriches the grand tale of our cosmic origins, a narrative where the densest matter and the vastest expanses unfold as interconnected chapters. Throughout history, humanity's innate curiosity has driven us to explore the deepest mysteries of the natural world, pushing the boundaries of knowledge far beyond the horizons of immediate experience. In this grand tradition, understanding what lies hidden in the core of a neutron star represents a profound quest, not only to uncover the secrets of these cosmic remnants, but also to unlock fundamental physics that governs matter, energy, and the fabric of the universe itself. This pursuit epitomizes the power of human curiosity to connect the infinitesimally small and the cosmically vast, weaving a narrative of discovery that resonates throughout science and philosophy. The core of a neutron star embodies one of the universe's most extreme laboratories, where matter is compressed to densities exceeding those achievable in terrestrial experiments by orders of magnitude, and where gravity, quantum mechanics, and nuclear forces collide in a delicate dance. By peering into this exotic realm, scientists seek to test and refine the fundamental laws of physics, probing the strong nuclear force under extreme conditions, exploring novel phases of matter, and confronting the limits of quantum degeneracy and general relativity. Unlocking these secrets promises insight into questions that bridge disciplines. How do subatomic particles behave when squeezed beyond conventional limits? What states of matter exist at ultra-high densities? And how does gravity reconcile with quantum phenomena? Moreover, neutron star cores serve as cosmic crucibles that directly impact our understanding of the universe's evolution. From the birth of heavy elements essential for life to the mechanisms powering distant explosions and gravitational wave signals, the physics within neutron stars connects to fundamental cosmological processes. By deciphering their interiors, we unravel pieces of the grand cosmic puzzle: the synthesis of matter, the dynamics of compact objects, and the evolution of the cosmos itself. On a human level, this intellectual adventure reflects our species' relentless drive to comprehend the unknown. Each theoretical hypothesis, observational breakthrough, and experimental effort to simulate neutron star conditions embodies the ceaseless curiosity that propels scientific progress. It is a journey that transcends practical applications, inspired instead by the profound desire to understand our place in the universe and the laws that govern it. In essence, the study of neutron star cores is a testament to the unity of knowledge, that by exploring the densest stars, we illuminate the laws that shape not only distant realms, but also the fundamental fabric of reality. It is a reminder that curiosity is a powerful force, one that bridges scales from quarks to quasars, and fuels humanity's ongoing exploration of the cosmos and ourselves. As our understanding of neutron stars and their enigmatic cores continues to deepen, the horizon of discovery stretches ever further, beckoning with unresolved mysteries and tantalizing possibilities. The frontier ahead is a domain where technological innovation, theoretical insight, and observational prowess converge to unlock answers hidden in the densest and most extreme objects in the universe. Future telescopes and detectors promise to transform our grasp of neutron stars, revealing details once thought inaccessible and propelling the quest for fundamental physics into remarkable new territory. One of the most eagerly anticipated advancements lies in the next generation of gravitational wave detectors. Building upon the pioneering successes of LIGO, Virgo, and KGRA, forthcoming observatories like the Einstein Telescope in Europe and the Cosmic Explorer in the United States aim to deliver dramatically enhanced sensitivity. These facilities will extend detection ranges, unravel the intricate waveforms emitted by neutron star mergers with unprecedented precision, and uncover a richer variety of merger events. By probing the subtleties of tidal effects, mass distributions, and post-merger oscillations, these instruments will sharpen constraints on the neutron star equation of state and explore phenomena such as quark deconfinement and exotic phases within merger remnants. Simultaneously, advances in X-ray astronomy herald transformative potential. Missions like NASA's proposed Lynx X-ray Observatory or ESA's Athena are designed to achieve extraordinary spatial and spectral resolution. They will scrutinize neutron star surfaces, map hotspots, and perform detailed spectroscopy of thermal and magnetospheric emissions. These observations will enable highly precise measurements of neutron star radii and masses, enhancing our capacity to test fundamental physics and identify signs of superfluidity, superconductivity, or crustal phenomena like nuclear pasta. Radio astronomy also stands at the brink of a revolution, driven by facilities such as the Square Kilometre Array, SKA. The SKA's unprecedented sensitivity and sky coverage will discover vast numbers of new pulsars, including those in compact binaries, and perform exquisitely detailed timing measurements. Such data will enrich gravitational wave detection via pulsar timing arrays, shed light on neutron star interior dynamics, and potentially uncover continuous gravitational waves emitted by spinning neutron stars with asymmetries. On the neutrino frontier, future large-scale detectors, including Hyper-Kamiokande and the Deep Underground Neutrino Experiment, DUNE, aim to capture neutrinos from nearby supernovae and neutron star mergers, providing unique insight into the dense matter environments and cooling mechanisms. Neutrino observations from such cataclysmic events will complement electromagnetic and gravitational wave data, completing the multi-messenger picture vital for deep understanding. Beyond observational platforms, advancements in computational astrophysics and nuclear theory promise to fortify interpretation and prediction. High-performance simulations integrating relativistic hydrodynamics, nuclear microphysics, and neutrino transport are growing increasingly sophisticated, enabling detailed modeling of neutron stars, their interiors, and merger dynamics. These theoretical tools assist in decoding complex data signatures, guiding experimental design, and refining models of matter under extreme conditions. Finally, interdisciplinary collaborations between astrophysicists, nuclear physicists, particle physicists, and gravitational theorists will be crucial. The upcoming convergence of empirical data with theoretical frameworks offers hope of resolving long-standing questions surrounding the maximum mass of neutron stars, the presence of exotic phases like color superconductivity, and the nature of matter beyond neutron degeneracy. In sum, the frontier ahead is vibrant and promising. Future telescopes and detectors across the electromagnetic spectrum, gravitational wave observatories with augmented reach, neutrino observatories capturing subtle cosmic whispers, and advanced theoretical models form an integrated global effort to peel back the layers of neutron star mystery. As humanity's observational and intellectual tools reach ever greater heights, they illuminate a path toward deeper answers. Answers that promise not only to unravel the secrets of neutron star cores, but also to enrich our fundamental understanding of physics, the cosmos, and our place within it.